Hey calculus folks, doing a little notes here on section 4.4 concavity, which sounds kind of weird. Sounds kind of like what a prisoner would do when they need to go to the dentist. That's pretty good, isn't it? I like to start off with a really good joke. Anyway, so last section, that was section 4.3, we used the first derivative, or we just called it the derivative, to determine when a graph was increasing or decreasing. So when was it going up, when was it going down, from left to right. Now today, with section 4.4, we're going to use the second derivative to determine whether or when a graph is concave up or concave down. Now, if you didn't do the 4.3 notes or stuff, you're going to get lost. So go back and do those now. All right, so what the heck is concave up and what is concave down? It doesn't have to do with whether the graph is going up or down. It has to do with the curvature of the graph. So what does concave up look like? Well, I have a good way to remember this. A graph, when it's curved up, see, sometimes it's going down and sometimes it's going up, but this whole thing, this whole chunk of the graph is concave up. And I always say, you remember concave up like a cup. Up like a cup, right? Because if you think about it, if you put water in there, it would hold it. If it's concave up, it'll hold some water. Granted, sometimes it doesn't look like a full cup. We'll look at some pictures of that later. But concave down would look something like this. It doesn't mean is the graph going up or down. See how it's going up here? It's going down there. So if it's like this, it's concave down like a frown. So up like a cup, down like a frown. That's pretty clever, isn't it? So anyway, that's what it looks like. Now you can have graphs that change, right? And you can have a graph that's like, starts off like that, it goes like that, right? That's like the x cubed graph, right? Well, if you look at this, for this chunk, it's down like a frown. I mean, you'd have to use your imagination to like see the rest of the frown if you're a pessimist. And then this part from here to here is up like a cup. You can kind of, if you imagine extending that curvature out. This graph is increasing the whole time, so it doesn't have anything to do with the first derivative. But if we use the second derivative, you can actually figure out when a graph switches back and forth. So let's draw another quick picture of one. Okay, so let me get a picture here just to save some time. All right, so on this one, if you just have a crazy looking graph, we can determine where is it concave up and where is it concave down. So when I'm looking at this, I'm not looking for where is it increasing, because if I was doing increasing, I would say from negative infinity to -3, my graph is going up. And then from -3 to 2, it's going down. From 2 to 4, it's going up again, and then it starts going down again. So basically, that would be if I asked you to determine the increasing or decreasing from a graph, which wouldn't be that hard. You're just like, am I going uphill or am I going downhill? Uphill, downhill. But if I'm doing concavity, I just want to look at its curvature. Is it down like a frown or up like a cup? And if I look at this first chunk of the graph, this whole chunk is down like a frown from here to here, right? And then it's up like a cup from here to here, and then it starts to frown again. It gets sad. It's on an emotional roller coaster, like we all are. It's 2020, man. All right, so on this one, since it's down like a frown, this would be concave down. and this would be concave up, this would be concave down. So we go, okay, so it's concave up from 0, and we just talk about x values, 0 to 3. It's concave down from negative infinity to 0, and there's my union, and from 3 to infinity. Okay, so that's just what it looks like. Now, there must be a special name for these points where it switches from concave down to concave up, or from concave up to concave down. These are called inflection points, where a graph changes concavity. What were they called when it changes from increasing to decreasing, or decreasing to increasing? They were called extrema, your max and mins. Well, these ones have special names too. They're called inflection points. Next time you look at your spoon, right? Most spoons have an inflection point because they go down like this, and they come back up. Just trust me, it's a spoon. Ooh. Nice spoon, thank you. All right, so you can tell it's down like a frown. There's an inflection point like right here, and it starts curving the other way. Okay, next time you're eating, just think about the inflection points. Think about the inflection points, people. Looks good. You have some soup, right? You got a bowl. Make some Tuscan soup, maybe some tortilla soup. Have a good pumpkin soup recipe if you want. All right, so, well, I digress. So here's our rules. If the second derivative is greater than 0, your graph is concave up, like a cup. If your second derivative is less than 0, you're concave down, like a frown. And if your second derivative equals 0, you have an inflection point. That's where it switches. So that's kind of cool. That's pretty neat. So we'll do some problems where you have to do it all. It'll be a refresher of last time too. All right, so we're going to do this next example to determine the intervals when f of x is concave up or concave down, and find any inflection points. So when you're talking about concavity and inflection points, I need the second derivative. So how do you get a second derivative? Well, you take a first derivative, right? And then you take the derivative of that, and you get to the second derivative. So we got 3x squared, so 6x plus 8. So, you know how we had critical numbers were when the first derivative equaled 0, or undefined. Inflection points happen when the second derivative equals 0. So kind of your steps are, you need to find the second derivative, look for inflection points, or when f prime, double prime, we call that double prime, equals 0, and you just set it equal to 0, right? And solve it. So negative 8 equals 6x, x equals negative 8 over 6, or negative 4/3, which is negative 1.3 repeating. Now, what do we do with that? Well, kind of like last time, I think it's easiest to set up a table real quick. This table only needs to split right here. I already know there's going to be an inflection point at when x is 4/3. So my graph is going to split at x equals 4/3, negative 4/3, which means my interval, my graph is just split down the middle. So the left side is from negative infinity to negative 4/3. The right side is negative 4/3 to infinity, the whole rest of the graph. Then, kind of like before, you can pick any point you want to test on that interval. So -4/3 is a little over -1, so how about -2? -2 falls between those two numbers. What falls between these two numbers? Well, the easiest number for me to plug in is 0. You could have picked anything. You could have picked 5. Because what's neat is you are going to use the second derivative test, which means you just plug your test point into the second derivative and see if the answer comes out positive or negative. So I'm going to plug in a -2 to my second derivative here, and I'm going to plug in a 0 to my second derivative here. So if I plug a -2 in here, you get -2 times 6 is -12, plus 8 is -4. I really only care that it's negative. I plug a 0 in, 0 times 6 is 0, you get 8. I only care that it's positive 8. Because if it's negative, this is where you determine is it concave up or concave down. If it's negative, you're going to say, okay, that's concave down. If it's positive, it's concave up. And then I want a picture. Concave down like a frown, concave up like a cup. And that means there's an inflection point at -4/3, comma. Now, how do you find the y part? Well, you plug it in to that equation. So you'll do -4/3 cubed plus 4x squared minus 1. Pretend you did that, and you get 101 over 27, which is about 3.7. So there's an inflection point there, and we have concave up from -4/3 to infinity. We have concave down from -infinity to -4/3. There, we answered the question. Awesome. I almost forgot. I should always do this. I like to look at the graph to see if it really looks like that. Remember, we were just finding where it's curving up and curving down. So if I look at the graph of this, it should be down like a frown until -4/3. -4/3 is like a little past -1, so like right there. See how it's down like a frown until that little place right in the middle there? And then from then on, it's up like a cup. And there's an inflection point right at -4/3. Let me see if I can, what do you do? Trace, and then you type in the x you want, -4/3. There, I put the dot right there. Look where it's blinking. That looks like it is exactly where it switches over. So it's always good to look at a graph, but we figured that out without needing a graph. All right, so I'm going to come back and do the other part of this, which is not hard, but a couple more examples would probably make it sink in a little better. This is the main idea, though. There is something called the second derivative test, which I'll show you in a second.